There's something haunting about standing before a wall of ice, not just for its sheer, breathtaking scale, but for what it hides within. Picture this: ancient layers of frozen time, stacked like pages in a book no one knew existed. And now, as the planet warms and these icy barriers crack open, they're revealing Earth's oldest, most forgotten stories. This isn't just melting ice, it's a library of lost climates, a hidden archive of our planet's turbulent past. Every layer, every bubble of trapped air, holds secrets about the world as it once was, long before humans walked its surface. And what we're finding could rewrite everything we thought we knew about Earth's future. For centuries, these towering ice walls seemed like silent sentinels, unchanging and eternal. But the truth is far more extraordinary. Deep within their frozen depths lie records of ancient storms, vanished ecosystems, and atmospheric shifts that shaped life itself. Think of them as time capsules, preserving snapshots of the planet's mood, swings from ice ages to tropical epochs, all waiting to be read. Scientists are now racing to decode these icy manuscripts before they vanish forever, piecing together puzzles that stretch back hundreds of thousands of years. And what they've uncovered so far is nothing short of astonishing. Proof of civilizations rising and falling with the climate, of oceans swallowing coasts, and of entire species adapting or disappearing in the blink of geological time. This is more than just a tale of ice and data. It's a window into the fragility of our own world, a reminder that the planet's climate has never stood still. The stories trapped in these frozen vaults don't just belong to the past, they're urgent messages about the future. Because if there's one thing these ancient ice walls are telling us, it's that change is the only constant. And as we stand at the edge of these crumbling archives, we're not just observers, we're the next chapter in Earth's story. So let's step inside this icy library together and uncover what it means for all of us. The answers, it turns out, have been frozen in time waiting. To unlock the secrets buried in these ancient ice walls, scientists rely on an extraordinary tool: ice cores. Imagine taking a giant straw and drilling straight down through layers of ice that have built up over hundreds of thousands of years. Each core pulled from the depths is like a time machine, preserving tiny air bubbles, volcanic ash, and even traces of pollen, frozen snapshots of Earth's past. These pristine records are so detailed that researchers can pinpoint years when massive eruptions darkened the skies, or when sudden shifts in temperature reshaped entire ecosystems. The real magic happens in the lab, where scientists analyze the chemistry of these ice layers with precision that borders on poetry. By measuring isotopes, different forms of oxygen and hydrogen atoms, they can reconstruct past temperatures with remarkable accuracy. Think of it like reading a thermometer frozen in time. Deeper still, those tiny air bubbles trapped before the pyramids were built hold ancient atmospheres. They reveal how carbon dioxide and methane levels have risen and fallen, long before humans started burning fossil fuels. Even dust particles tell stories, hinting at ancient droughts or winds that carried minerals across continents. But here's what's truly mind-blowing. These ice cores don't just show natural cycles. They capture humanity's fingerprint on the planet. In younger layers, scientists find spikes in lead from Roman smelting, soot from Industrial Revolution factories, and even radioactive fallout from mid-century nuclear tests. It's as if the ice itself has been keeping receipts, documenting every major shift, natural or man-made. And that's why these frozen archives are so urgent today. By understanding how Earth's climate responded to past changes, we're not just piecing together history, we're getting a preview of what might come next. The hunt for Earth's frozen history began in earnest during the 1950s and 60s, when teams of researchers launched daring expeditions into the planet's most inhospitable frontiers. Armed with little more than hand-cranked drills and sheer determination, these pioneers ventured onto the vast ice sheets of Greenland and Antarctica, where temperatures could plunge to 70 below zero and winds howled with enough force to knock grown men off their feet. They weren't just exploring geography, they were tunneling through time itself. What they pulled from those frozen depths rewrote the textbooks. Early ice cores revealed layers dating back over 100,000 years, capturing snapshots of climates when mammoths still roamed and Neanderthals thrived. But as drilling technology improved, the records kept growing older 200,000 years, then 400,000, and eventually nearly 1,000,000 years of Earth's atmospheric history locked away in shimmering blue ice. Each meter drilled downward was like turning another page in the planet's diary, with older entries written in increasingly cryptic chemical signatures. The real breakthrough came when researchers noticed something peculiar in these ancient layers, rhythmic patterns of lighter and darker ice, like tree rings for the planet. These bands corresponded to subtle shifts in Earth's orbit and tilt, proving for the first time how intimately our climate dances to celestial rhythms. But nestled between these predictable cycles were violent surprises, layers of volcanic ash from eruptions so massive they dimmed the sun for years, or sudden temperature spikes that reshaped continents in mere decades. It was proof that our planet's climate doesn't just change, it lurches, stumbles, and occasionally reinvents itself overnight. Perhaps most astonishing was how these frozen records connected to human history. One team studying Greenland's ice found lead pollution from ancient Roman smelters, preserved in layers dating back to the height of the empire. Another discovered traces of medieval plagues written in atmospheric chemistry. When populations crashed, forests regrew, pulling carbon from the air and leaving telltale markers in the ice. The walls weren't just recording natural history, they'd been silently documenting our rise, our mistakes, and our impact on the world long before we realized we were leaving a trace. Now, as these icy archives melt at an alarming rate, scientists face a race against time to preserve what remains. Each summer, more of this irreplaceable climate library liquefies into oblivion, taking with it secrets we've only begun to decipher. The irony is profound. The very warming that threatens these records is also making them more crucial than ever to understand, because hidden in their crystalline depths may lie the answers to our most pressing question: just how resilient is Earth's climate system when pushed to its limits? The ice walls have watched civilizations rise and fall before. What they whisper next could determine whether we listen in time. Those tiny air bubbles trapped in the ice aren't just empty pockets, they're minuscule time capsules, each one holding a breath of Earth's ancient atmosphere. Picture cracking open a bubble that formed during the last ice age and inhaling air that hasn't circulated since woolly mammoths walked the tundra. Inside these frozen whispers, scientists find the very gases that shape our planet's thermostat: carbon dioxide and methane, preserved with astonishing precision. What these bubbles reveal is nothing short of revolutionary, a direct chemical record proving that greenhouse gases and global temperatures have danced in lockstep for hundreds of thousands of years. The patterns etched in this icy ledger are unmistakable. During cold periods like the last glacial maximum around 20,000 years ago, when ice sheets stretched as far south as New York City, the bubbles show carbon dioxide levels hovering around 180 parts per million. But when Earth warmed into interglacial periods like the one we're in now, those numbers climbed to 280 or higher. This wasn't just coincidence, it was climate chemistry in action, with greenhouse gases acting like a planetary blanket, trapping heat when concentrations rose and letting it escape when they fell. The ice cores captured this relationship so clearly that researchers could trace how even small fluctuations, just a few dozen parts per million, meant the difference between glaciers carving valleys and hippos swimming in the Thames. Methane tells an equally compelling story. While carbon dioxide lingers for centuries, methane is the flashier, more potent greenhouse gas, packing 30 times more heat-trapping power in the short term. The ice reveals how methane levels spiked dramatically during periods of sudden warming, often released from thawing permafrost or bubbling up from ocean sediments. These weren't gradual changes. Either cores from Greenland show methane concentrations sometimes doubling in mere decades, proving that Earth's climate doesn't always shift at a glacial pace. What makes these frozen records so invaluable is their impartiality. Unlike computer models or theoretical calculations, the ice simply presents the facts, layer after layer of incontrovertible evidence showing how our planet's climate system actually behaved under different conditions. And the conclusion is inescapable. Whenever carbon dioxide levels reached where they are today, over 400 parts per million, global temperatures were significantly higher, sea levels were meters above current marks, and the world looked utterly different. The last time concentrations were this high was during the Pliocene epoch 3 million years ago, when palms grew in the Arctic and oceans lapped at the foothills of today's coastal cities. Yet there's one glaring difference between then and now. Past rises in greenhouse gases unfolded over thousands of years, giving ecosystems time to adapt. The spike we're seeing today has happened in little more than a century, a geological blink of an eye. The ice cores show us what equilibrium looks like at these gas levels, but they also sound a silent alarm. We're conducting an unprecedented experiment with the only atmosphere we've got. As these frozen archives continue to melt away, they leave us with both a warning and a challenge to read their ancient writing before it vanishes, and to heed what it tells us about the fragile balance that sustains us all. Volcanic eruptions don't just shape landscapes, they rewrite the very chemistry of our atmosphere, and ice cores have preserved their dramatic signatures like pages in a geological crime scene. When a volcano explodes, it blasts millions of tons of ash and sulfur dioxide high into the stratosphere, where winds spread these particles across the globe. Over time, they rain down onto ice sheets, leaving behind razor-thin gray lines, ghostly echoes of Earth's most violent outbursts. But these aren't just static records. Scientists can read them like barcodes, extracting details about the eruption's power, location, and even the precise year it occurred. Take the cataclysmic eruption of Mount Tambora in 1815, which unleashed so much sulfur dioxide that it formed a sun-blocking haze around the planet. Ice cores from both poles captured this event as a vivid spike in acidity, a chemical scream frozen in time. The fallout was immediate, temperatures plummeted, crops failed across Europe and North America, and snow fell in New England during July. Journals from the era describe it as the year without a summer, but the ice tells an even deeper story. By comparing sulfur deposits in cores from Greenland and Antarctica, researchers traced how the volcanic veil circled the globe, lingering for nearly 3 years and disrupting weather patterns as far away as India. Some ice layers reveal eruptions so ancient they predate human memory. One core drilled in Antarctica uncovered traces of a super-eruption 74,000 years ago, when Sumatra's Toba volcano ejected enough material to bury entire states. The ice showed sulfur levels 6 times higher than Tambora's, suggesting decades of volcanic winter that may have pushed early humans to the brink. Other cores hold clues to more mysterious events, like a massive sulfur spike around 540 AD, coinciding with accounts of an 18-month-long mystery cloud darkening Europe and Asia. Historians once dismissed these tales as myth, but the ice proves something colossal really did blot out the sun. What makes these volcanic fingerprints so valuable isn't just their ability to date ice layers, it's how they reveal Earth's delicate climate balance. A single eruption can temporarily cool the planet by reflecting sunlight back into space, masking the warming effects of greenhouse gases. But the ice cores also show these events are short-lived. Within years, the sulfur rains out and temperatures rebound. Unlike today's human-driven warming, which keeps intensifying, volcanic cooling is nature's fleeting fever break, a reminder of how profoundly different natural and human influences can be. Now, as researchers drill deeper into ice that's millions of years old, they're uncovering eruptions from epochs when Earth's climate was radically different. These ancient layers may hold answers to one of geology's biggest puzzles: whether volcanic activity helped trigger or accelerate past mass extinctions. Every ash band, every sulfur spike is another piece of the planet's epic survival story, one where fire and ice have danced together since long before humans took the stage. And as our own era of climate change unfolds, these frozen volcanic warnings remind us, Earth's systems are resilient, but they operate on scales that humble even our greatest civilizations. Those microscopic dust grains embedded in ancient ice might seem insignificant at first glance, just specks of sand or silt frozen in place. But peer closer, and each particle becomes a tiny messenger from Earth's distant past, carrying secrets about winds that howled across continents long before written history began. When scientists examine these trapped grains under microscopes, they're not just looking at dirt, they're deciphering weather reports from millennia ago. The size, shape, and mineral composition of each speck reveal where it came from, whether it was ripped from the Sahara's dunes, scraped off Himalayan peaks, or flung skyward by drying lake beds. Together, these invisible fragments map ancient jet streams and monsoons with startling precision, showing how Earth's atmospheric highways have shifted over time. One of the most startling discoveries hidden in this icy dust is evidence of mega-droughts, periods when deserts expanded for centuries, turning fertile regions to dust. In ice cores from the Andes, researchers found layers packed with minerals from Bolivia's Altiplano, proof of winds scouring what was once a lush wetland. Around 3,800 years ago, the same dust appears in cores from Greenland, carried there by global wind patterns. This wasn't just a local dry spell, it was a planetary-scale rearrangement of moisture, one that archaeologists now link to the collapse of Bronze Age empires from Mesopotamia to the Indus Valley. The ice preserves these climate catastrophes in exquisite detail, like a forensic report written in mineral fingerprints. But dust does more than mark disasters. It also reveals how interconnected our planet's systems truly are. When glaciers advanced during ice ages, ice cores show spikes in dust from dried-up river valleys and exposed continental shelves. As the world grew colder, it also grew drier, with fierce winds lifting billions of tons of sediment into the atmosphere. Some of this dust became the nucleus for snowflakes, falling back onto ice sheets in a self-reinforcing cycle. Other particles traveled astonishing distances. Cores from Antarctica contain dust from Australia's outback, proving that even the most remote corners of Earth are linked by invisible aerial rivers. Perhaps most remarkably, this ancient dust helps solve historical mysteries. In ice layers dating to the 9th century, scientists found traces of lead pollution alongside Saharan minerals, evidence of trans-Saharan trade routes where caravans carried silver and other goods across the desert. Other cores hold volcanic ash from Iceland mixed with Mongolian dust, showing how medieval storms could blend materials from opposite ends of the globe. Even the decline of Rome leaves a trace. Layers from around 500 AD show a sudden drop in lead dust, coinciding with the empire's economic collapse. Today, as modern deserts expand and dust storms intensify, these frozen records take on new urgency. They show us that civilization has always been at the mercy of the winds, and that when droughts come, their effects ripple across continents. The next chapter of this story is being written right now as modern particles settle onto glaciers. Future researchers may one day study our era's dust, finding microplastics, industrial metals, or ash from wildfires, a new kind of climate archive recording how we change the very air itself. The ice cores hold a sobering record of humanity's rise, not written in words but in chemicals. As you move upward through the layers, something startling happens. Around the mid-1800s, pristine ice suddenly darkens with streaks of lead and mercury, as if the planet itself began bleeding industrial toxins. These aren't natural deposits. They're the unmistakable signature of the Industrial Revolution, a time when humanity learned to reshape the world and left its mark in the very ice of Antarctica and Greenland. One particularly stark line appears in ice dated to 1880, coinciding with the explosion of coal-fired factories and smelters. The lead concentration in that single layer is 30 times higher than anything seen in the previous 80,000 years. What's chilling isn't just the presence of these pollutants, it's how abruptly they appear. For millennia, the ice had recorded only the slow, rhythmic pulses of natural cycles. Then, in a geological instant, human activity drowns out every other signal. Take mercury, a metal once used recklessly in hat-making and gold extraction. Ice cores show its levels tripling between 1850 and 1900, then doubling again by 1950. These aren't gradual changes, they're vertical spikes on the graph, like a fever chart for a planet suddenly running hot with industry. Even more telling, the pollutants spread globally almost immediately. Cores from remote Himalayan glaciers show the same lead peaks as those from the Alps, proof that no corner of Earth remained untouched. But the ice doesn't just catalogue our mistakes, it also documents our occasional wisdom. In the 1970s, as nations began banning leaded gasoline, the ice recorded something extraordinary, a sudden drop in lead concentrations. It's a rare bright line in an otherwise grim ledger, showing that when humanity acts collectively, we can alter our environmental trajectory. Similar dips appear after international agreements on mercury and sulfur emissions, each policy shift preserved in the frozen strata like geological receipts for planetary repairs. Yet the most haunting revelation lies deeper in the ice. When scientists compare pre-industrial layers to modern ones, they find something unsettling. Today's atmosphere holds more carbon dioxide than at any point in the last 800,000 years. Not gradually more, wildly more. The increase since 1950 alone exceeds what once took millennia. It's as if Earth's climate history, written patiently over eons, has been scribbled over in bold, urgent strokes. These frozen archives don't judge or warn, they simply testify. And what they're telling us is that we're not just passing through geological time, we're rewriting it. The secret to unlocking Earth's ancient climate isn't just hidden in the ice, it's written in the very atoms that make up each frozen molecule. When scientists examine ice cores, they're not just looking at frozen water. They're reading a delicate atomic code, where the ratio of oxygen's different forms, isotopes, acts like a precision thermometer from the distant past. Here's how it works. Oxygen atoms come in slightly different weights, with oxygen-16 being lighter and oxygen-18 heavier. During warm periods, evaporation favors the lighter isotope, leaving more of it trapped in snowflakes that eventually compress into ice. But when temperatures drop, heavier oxygen-18 becomes more common in snowfall, creating a clear chemical signature of cold. This subtle atomic dance has allowed researchers to reconstruct temperature records with astonishing detail, tracking fluctuations down to fractions of a degree over hundreds of thousands of years. Imagine being able to read the weather report from a day 75,000 years ago, not in vague estimates, but with the same precision as modern instruments. That's the power locked in these isotopic patterns. One of the most striking revelations from this data is just how tightly global temperatures have mirrored changes in greenhouse gas concentrations across 8 glacial cycles. When carbon dioxide levels dipped during ice ages, oxygen isotopes show the world cooling in lockstep. And when gases rose during warm interglacial periods, the isotopic record reflects the sudden thaw. But the real genius of this method lies in its cross-verification. Oxygen isotopes in ice don't just tell one story, they echo across multiple climate archives. The same isotopic signatures appear in fossilized plankton shells from ocean sediments and in mineral deposits from ancient caves, creating a web of corroborating evidence. When ice cores from Antarctica show a temperature spike 50,000 years ago, stalagmites from China's caves often reflect the same event, proving these weren't local anomalies but planetary shifts. Some of the most fascinating details emerge when scientists zoom in on abrupt climate transitions. In Greenland's ice, oxygen isotopes reveal that the end of the last ice age wasn't a gradual warming. It came in violent lurches, with temperatures soaring as much as 10 degrees Celsius in a single decade. These aren't theoretical models or best guesses. They're physical measurements written in atomic chemistry, showing that Earth's climate can pivot with breathtaking speed when pushed past certain thresholds. Now, as modern temperatures rise, these frozen isotopic records take on new urgency. They show us that the current warming trend stands far outside natural variability, both in its speed and its global uniformity. Unlike past climate shifts, which saw different regions warm or cool at different rates, today's warming leaves its mark simultaneously in ice cores from the Andes, the Alps, and the Arctic. The atomic thermometers of the past are sounding an unmistakable alarm. What's happening now isn't just another cycle. It's something fundamentally new, and the ice holds the proof. Methane is the ghost in Earth's climate machine, a silent, potent force that appears suddenly in the ice core records, then vanishes just as quickly. Unlike carbon dioxide, which lingers for centuries, methane operates in quick, dramatic bursts, leaving behind jagged spikes in the frozen archives. These aren't gradual rises, they're abrupt surges, sometimes doubling atmospheric concentrations in just decades. And what makes them so fascinating and unsettling is how often they coincide with moments when the planet was already warming. It's as if Earth's climate has hidden tripwires, and methane is the spark that kicks change into overdrive. Take the Younger Dryas period around 12,000 years ago, a time when the world was emerging from an ice age. Just as temperatures began climbing, ice cores reveal a colossal methane spike, one that far outstrips anything seen in the previous 50,000 years. Where did it come from? Scientists point to thawing permafrost and expanding wetlands as likely culprits. As the planet warmed, vast stretches of frozen ground softened, releasing bubbles of methane trapped for millennia. Meanwhile, rising temperatures and heavier rains transformed dry landscapes into sprawling marshes, where decomposing plants pumped even more methane into the air. This created a feedback loop. Warming released methane, which accelerated warming, which released more methane. The ice cores capture this cycle in stunning detail, showing how small shifts can snowball into planetary-scale transformations. But the real mystery lies in how quickly these changes unfolded. In Greenland's ice, some methane spikes are so abrupt they span just a few annual layers, proof that Earth's climate doesn't always move at the stately pace we imagine. One theory suggests that certain regions, like the Arctic's submarine permafrost, may hold reservoirs of methane in an unstable form called clathrates. When temperatures cross a threshold, these icy cages shatter, releasing gas in sudden, explosive belches. Imagine uncorking a shaken soda bottle, but on a continental scale. While the full story remains debated, the ice leaves no doubt. When methane speaks, the climate listens. What's especially revealing is how these ancient methane surges mirror what's happening today. Satellite data shows modern methane levels rising at an unprecedented clip, with contributions from thawing permafrost, industrial activity, and even livestock. The difference past spikes played out over centuries. Today's climb is happening in decades. And just like in the ice core records, these increases aren't just a symptom of warming, they're fuel for it. Every molecule of methane traps heat dozens of times more effectively than carbon dioxide, making it a turbocharger for climate change. The lesson from these frozen bubbles is clear. Methane isn't just a passenger on Earth's climate journey, it's a driver capable of yanking the wheel when we least expect it. And as scientists drill deeper into older ice, they're finding even older methane spikes, each one a clue to how our planet's systems can suddenly and dramatically flip. The past whispers that small nudges can have outsized consequences. The question now is whether we'll heed that warning before the next great surge begins. The Younger Dryas stands out in ice core records like a jagged lightning bolt across an otherwise smooth graph, a violent detour in Earth's climb out of the last ice age. Just as global temperatures were steadily rising 12,000 years ago, something extraordinary happened. Within decades, a blink in geological time, the planet lurched backward into bitter cold. Ice cores from Greenland tell the story in stark chemical shifts. Oxygen isotopes plunge, dust concentrations skyrocket, and methane levels collapse. Forests that had been creeping northward suddenly retreated, ice sheets advanced again, and temperatures in some regions dropped a staggering 10 degrees Celsius. This wasn't just a cold snap, it was a full-scale climate rebellion that lasted over 1,000 years. What could trigger such a dramatic reversal? One leading theory points to Earth's plumbing, specifically the massive freshwater lakes left behind by melting glaciers. As the Ice Age waned, an enormous glacial lake covering much of what's now Canada grew unstable. When its icy dam finally burst, a deluge equivalent to several hundred Amazons poured into the North Atlantic. This freshwater flood may have shut down the ocean's conveyor belt of currents, including the Gulf Stream that warms Europe. Without this heat pump, the Northern Hemisphere plunged back into winter. The evidence, ice cores show salt levels in Atlantic sediments dropped precisely when the cooling began, as if someone pulled the plug on the planet's heating system. But there's another contender in this climate whodunit space. In sediment layers dating to the Younger Dryas onset, scientists have found nanodiamonds, melted glass, and other exotic materials often linked to cosmic impact. Some researchers propose that a comet or asteroid exploded over North America, igniting wildfires across continents and lofting enough soot to dim the sun. Ice cores from that period do show a mysterious spike in ammonium and nitrate chemical fingerprints of burning biomass. Yet the impact theory remains hotly debated, with critics noting that similar particles appear in volcanic layers, and no single large crater has been definitively tied to the event. The most unsettling lesson from the Younger Dryas isn't just what caused it, but how fast it unfolded. pollen records show ecosystems scrambling to adapt, with some plant species migrating hundreds of miles in mere generations. For early human societies like the Clovis people of North America, this climate whiplash coincided with the disappearance of megafauna mammoths, giant sloths, and other Ice Age icons. Whether due to hunting pressure or vanishing habitats, their decline mirrors the instability captured in the ice. What makes this ancient climate U-turn so relevant today is its demonstration of Earth's delicate balancing act. The Younger Dryas proves our planet's climate doesn't always change gradually. It can flip states abruptly when certain thresholds are crossed. And while we may never pinpoint a single culprit for this prehistoric climate rebellion, the ice cores leave no doubt. When Earth systems are disrupted, the consequences ripple through every forest, ocean, and civilization in their path. As we now steer the planet into uncharted territory, these frozen warnings from 12,000 years ago feel less like ancient history and more like a preview. The rhythmic heartbeat of Earth's climate pulses through the ice cores, a mesmerizing pattern of ice ages and warm interludes stretching back nearly 3 million years. These aren't random fluctuations, but a planetary metronome ticking in time with celestial mechanics. At the center of this grand cosmic dance are the Milankovic Cycles, 3 subtle orbital variations that dictate how sunlight kisses the Earth's surface. First, there's eccentricity, the shape of Earth's orbit around the Sun, which stretches from nearly circular to slightly elliptical over 100,000 years. Then axial tilt, which wobbles between 22 and 24.5 degrees every 41,000 years, altering the intensity of seasons. Finally, precession, the slow gyration of Earth's axis, like a spinning top winding down, completing a full cycle every 26,000 years. Individually, these changes seem insignificant. But together, they compose a climatic symphony, conducting the advance and retreat of glaciers with astonishing precision. The ice cores capture this symphony in exquisite detail. In layers dating to Ice Age peaks, oxygen isotopes reveal temperatures up to 10 degrees Celsius colder than today, while trapped air bubbles show carbon dioxide levels plunging to 180 parts per million, barely enough to sustain plant life. Then, with clockwork regularity, the records show sudden warm spikes, where greenhouse gases surge and ice sheets crumble back toward the poles. What's striking isn't just the pattern, but its timing. For the past million years, ice ages have arrived like clockwork every 100,000 years, matching Earth's eccentricity cycle with uncanny alignment. Before that, during the Pleistocene, the rhythm quickened to 41,000 years, mirroring the axial tilt cycle. It's as if the planet's climate has been tuning itself to celestial frequencies all along. Yet the real revelation lies in the feedback loops these orbital nudges trigger. When Milankovic Cycles slightly reduce summer sunlight in the northern hemisphere, snow lingers longer, reflecting more heat into space. This cools the planet further, allowing ice sheets to expand, which reflects even more sunlight, a runaway cooling effect preserved in the ice as a steep isotopic plunge. Conversely, when orbital alignment brings stronger summers, the process flips. Melting ice exposes dark land and ocean, absorbing heat and accelerating warming. The ice cores show these feedbacks amplifying tiny orbital changes into global transformations, proof that Earth's climate system is exquisitely sensitive to even gentle nudges. What makes these ancient rhythms so urgent today is how they frame our current climate experiment. For the past 12,000 years, we've enjoyed the stable warmth of an interglacial period, a rare golden age in Earth's history when civilizations could flourish. Based on orbital cycles alone, we should be nearing the end of this warm spell, with glaciers beginning their slow advance. But instead, greenhouse gases are soaring off the charts, overriding these natural rhythms. The ice cores remind us, when orbital cycles and greenhouse gases worked together in the past, they rebuilt the world. Now, we've uncoupled them, pushing the system into uncharted territory where the old rules may no longer apply. Hidden within the ice are whispers of ancient deluges and droughts, chemical fingerprints that reveal how rainfall patterns have shaped civilizations and ecosystems across millennia. Every snowflake that fell during the last ice age carried a unique signature, its hydrogen and oxygen atoms arranged in ratios that betray the temperature and humidity of long-vanished clouds. By measuring these isotopes in ice cores, scientists can trace not just how much it rained or snowed, but where the moisture came from, whether it traveled thousands of miles from tropical oceans or condensed over nearby mountain ranges. The results are astonishingly precise. Layers corresponding to decades of relentless monsoons show distinct isotopic lightness, while droughts leave behind concentrated, heavier isotopes like parched earth holding its last drops. One of the most dramatic examples comes from layers dating to the so-called 4.2 kiloyear event, a megod drought around 2200 BC that lasted nearly a century. Ice cores from the Andes and the Himalayas show sudden spikes in dust and salt particles during this period, evidence of shrinking lakes and relentless winds scouring dry lake beds. But the real story lies in the oxygen isotopes, which reveal that monsoon rains faltered across 3 continents simultaneously. Archaeological records from Egypt to Mesopotamia tell the same tale. Kingdoms collapsing, cities abandoned, and populations scattering like dust in the wind. The ice preserves these climate upheavals with chilling clarity, proving how tightly human fortunes are tied to the sky's generosity. Yet these frozen records also hold surprises. In Greenland's ice, researchers found traces of supercharged storms from the medieval warm period layers packed with sea salt and marine microorganisms flung far inland by hurricanes of unprecedented fury. Similar cores from Antarctica show opposite patterns, centuries when snowfall dwindled to a trickle, leaving behind paper-thin annual layers. The contrast is stark. Some eras brought too much water all at once, while others starved landscapes into silence. What's remarkable is how these shifts often preceded major historical turning points. The decline of the Maya, for instance, coincides with isotopic evidence of prolonged dry spells that turned reservoirs to mud and crops to tinder. Modern climate models now use these icy archives to test their predictions. When simulations of past rainfall patterns match the isotopic signatures in cores, it boosts confidence in forecasts for our warming world. And the news is sobering. Many regions that thrived during wet periods in the past are projected to dry dramatically in coming decades, while others may face storms of a magnitude the ice records suggest are possible but rare. The takeaway isn't just academic. These frozen precipitation records remind us that when the rain stops, or when it won't stop falling, civilizations have always been forced to adapt or collapse. As today's climate shifts accelerate, the ice whispers a warning we do well to heed. Water, in the end, writes the rules. The ice holds more than just Earth's secrets. It captures whispers from the sun itself. Deep within those frozen layers, scientists have discovered traces of a rare isotope called beryllium-10, formed when cosmic rays from distant supernova collide with our atmosphere. Normally, Earth's magnetic field shields us from these high-energy particles, but when the sun's activity wanes, its protective solar wind weakens, allowing more cosmic rays to bombard our skies. The result, spikes in beryllium-10 production, neatly preserved in ice cores like a celestial fingerprint. These minuscule particles tell a story far grander than their size suggests, a chronicle of solar moods stretching back millennia. During periods like the Maunder minimum in the 17th century, when sunspots vanished for decades, ice cores show beryllium-10 concentrations soaring. This wasn't just a solar hiccup, it coincided with the coldest stretch of the Little Ice Age, when frost fairs thrived on frozen Thames River and glaciers swallowed alpine villages. The correlation is striking. As cosmic rays increased, Earth chilled. But how? One theory suggests these particles seed low-lying clouds by ionizing atmospheric molecules, creating a planetary sunshade that reflects sunlight back into space. When solar activity plunges and cosmic rays surge, cloud cover may expand, cooling the planet like a dimmer switch on the sun's brilliance. Yet the sun's influence isn't always so gentle. In ice layers dating to 774 AD, researchers found a beryllium-10 spike so sharp it suggests a solar storm of unimaginable fury, likely 10 times stronger than anything recorded in modern times. Tree rings from that same year show radioactive carbon-14 spikes, while ancient texts describe blood-red skies visible worldwide for weeks. Had such an event occurred today, it could have fried satellites and power grids, plunging continents into darkness. The ice preserves these solar tantrums as cautionary tales, reminding us that our star's serenity is never guaranteed. What makes these cosmic records so valuable is their ability to disentangle natural climate drivers from human influence. While greenhouse gases dominate modern warming, the sun's subtle pulses captured in beryllium-10 show that its impact, though real, pales beside humanity's footprint. Over the past century, as temperatures soared, solar activity actually declined slightly, disproving claims that our star alone could explain today's rapid warming. The ice doesn't just document these forces, it weighs them, proving that while the sun writes some chapters of Earth's climate story, we're now holding the pen. As newer ice cores drill deeper into Antarctica's ancient ice, they're uncovering even older solar cycles, some lasting thousands of years. These patterns hint that the sun may have prolonged ice ages or supercharged interglacial periods, its faint rhythmic flickering amplified by Earth's own feedback loops. Yet amidst these celestial rhythms, one truth stands clear. Never in 800,000 years of ice core records has the sun driven changes as swift or profound as those unfolding today. The beryllium-10 whispers a humbling lesson. We are both stewards and students of a climate shaped by forces far beyond our atmosphere, yet increasingly within our hands. Black soot streaks in ice cores tell a fiery story, one of raging wildfires, ancient agricultural burns, and the slow creep of industrialization staining the planet's frozen record. These dark bands aren't mere blemishes. They're forensic evidence of how fire has shaped Earth's landscapes and atmospheres for millennia. When scientists examine these particles under microscopes, they're not just looking at carbon, they're reading a global diary of combustion, written in the ashes of forests, grasslands, and eventually coal-fired factories. The oldest layers reveal a rhythm dictated by nature alone. Charcoal particles from 20,000 years ago show sporadic spikes, evidence of lightning-ignited wildfires that swept across Ice Age savannas. These natural burns left behind a chemical calling card, levoglucosan, a sugar molecule produced when plant matter burns. What's fascinating is how these ancient fire cycles sync with climate shifts recorded in the same ice cores. During dry, warm periods, charcoal concentrations surge, while frigid epochs show barely a whisper of smoke. It's a pattern written in ash. Climate controls fire, and fire, in turn, reshapes ecosystems. Then, around 8,000 years ago, the record flickers with something new. Ice cores from Antarctica and Greenland simultaneously show a gradual uptick in soot, coinciding with humanity's discovery of agriculture. As early farmers cleared land by burning, their smoke traveled astonishing distances. One core from the Andes contains black carbon from Indonesian peat fires set 2,000 years ago, proof that human influence on the atmosphere became global long before the Industrial Revolution. The ice preserves these moments with startling clarity. Layers from Europe's medieval period show spikes in lead and soot overlapping with historical accounts of widespread forest clearance, while cores from Arctic ice capture the aftermath of Siberia's 16th century wildfires ignited by slash and burn farming. But the most dramatic change comes in layers dating to the late 1800s. Suddenly, the soot isn't just plant-based charcoal, it's packed with spherical particles unique to coal combustion. These industrial-era markers appear first in European ice cores, then spread worldwide like ink blots on a map. The quantities are staggering. By 1920, black carbon deposition in Greenland had increased tenfold from pre-industrial levels. And unlike natural wildfires, which ebb and flow with droughts, this pollution came in an unrelenting tide, winter and summer alike. The ice cores capture the moment humanity's relationship with fire shifted, from a tool for survival to an engine of industry burning fossilized sunlight locked away for millions of years. Modern layers tell an even more complex story. While industrial emissions declined in some regions after clean air laws, ice cores now show new signatures: black carbon from intensifying wildfires in drought-stricken forests, mixed with soot from agricultural burns in the Amazon and Southeast Asia. The frightening twist: these particles aren't just passive records, they actively accelerate ice melt when they darken glacier surfaces, absorbing sunlight that pristine snow would reflect. It's a feedback loop written in the very ice that preserves them. Fires release soot, soot melts ice, melting ice changes climates, and climate change breeds more fire. The lesson from these smoky archives is clear. For most of Earth's history, fire was a natural phenomenon, its rhythms set by climate and vegetation. But as the ice cores show, humanity didn't just harness fire. We weaponized it, scaled it, and ultimately globalized its footprint. Now, as we drill deeper into ancient ice, we're faced with an uncomfortable truth. The soot of our past is still writing itself into the planet's future, one dark layer at a time. Beneath the weight of millennia, trapped in icy prisons smaller than a grain of sand, lie organisms that defy time itself. Ice cores have revealed an astonishing secret. They're not just geological archives, they're frozen zoos of ancient microbes, perfectly preserved in suspended animation. Some of these bacteria and viruses have been locked away for hundreds of thousands of years, untouched by sunlight or liquid water, yet still holding the spark of life. When scientists melt these pristine ice samples, they've watched in awe as long-dormant microbes wake from their slumber, stretching metabolic limbs that haven't moved since woolly mammoths roamed the tundra. What makes these microscopic survivors so remarkable isn't just their age, it's their resilience. Many belong to extremophile families, organisms adapted to thrive in Earth's harshest corners. Some withstand crushing pressure deep under glaciers, while others metabolize iron or sulfur in oxygen-starved pockets within the ice. Their survival strategies read like science fiction, producing antifreeze proteins to prevent cellular damage, entering near-indestructible spore states, or even repairing their own DNA after millennia of radiation exposure. These aren't just curiosities, they're blueprints for life's tenacity, offering clues about how organisms might endure on icy moons like Europa or Enceladus. Yet alongside wonder comes caution. In Siberian permafrost, researchers have revived 30,000-year-old viruses still capable of infecting amoebas. While these ancient pathogens don't threaten humans, their existence raises a provocative question. Could melting ice release forgotten diseases? The scenario isn't pure speculation. In 2016, a heat wave in the Arctic thawed reindeer carcasses infected with anthrax spores from the 1940s, sparking an outbreak that hospitalized dozens and killed a child. If relatively recent pathogens can reawaken what might lurk in ice that's been frozen for epochs, the answer lies in the ice cores themselves. By studying layers where past warming events occurred, scientists can track how microbial populations shifted when temperatures rose before. Some cores show sudden blooms of algae or bacteria during ancient interglacial periods, suggesting melting ice doesn't just release microbes, it can create new habitats for them to thrive. Other layers contain puzzling genetic fragments, remnants of viruses with no modern counterparts. While most pose no danger, their very existence underscores how little we know about Earth's frozen microbiome. Perhaps the most profound lesson from these icy time capsules isn't about threats, it's about survival. The microbes persisting in glaciers and permafrost have weathered countless climate swings, outliving ice ages and volcanic winters. Their strategies, cooperation, dormancy, radical adaptation, offer humbling insights as we face our own planetary changes. They remind us that life persists in the unlikeliest places, rewriting its own rules across deep time. And as the ice retreats, revealing its microscopic prisoners, we're left with a paradox. The tiniest organisms may hold the biggest clues to life's past and its future. Greenland and Antarctica may both be frozen worlds, but their ice cores tell strikingly different stories about Earth's climate, past like two witnesses describing the same event from opposite sides of the planet. Drill into Greenland's ice and you'll find a record of drama, temperatures lurching up or down by 10 degrees Celsius in just decades, with violent swings preserved like a seismograph tracing planetary upheaval. Antarctic cores, by contrast, reveal a slower, steadier rhythm, changes unfolding over centuries or millennia, as if the southern hemisphere were breathing deeply while the north hyperventilated. This isn't just a curiosity, it's a revelation about how our planet's climate systems dance to different beats. The key to this hemispheric divide lies in the oceans. Antarctica sits like a fortress surrounded by the Southern Ocean's endless, churning waters, a vast heat sink that smooths out temperature spikes. Greenland, meanwhile, is more vulnerable, sandwiched between the volatile North Atlantic and Arctic. When freshwater from melting glaciers flooded into the North Atlantic during past climate shifts, as happened during the Younger Dryas, it could slam the brakes on ocean currents that ferry warmth from the tropics. Greenland's ice captures these shocks in real time, layers showing sudden isotopic plunges, like a patient flatlining during surgery. Down in Antarctica, the same events register as faint echoes, muted by the Southern Ocean's immense thermal inertia. But the differences go deeper than pace. Greenland's ice holds chemical fingerprints of nearby events, volcanic eruptions in Iceland, dust storms from Mongolian deserts, even lead pollution from medieval European silver mines. Antarctic cores, by contrast, are Earth's ultimate averaging machines, blending signals from across the southern hemisphere into a smoother narrative. Take the last ice age's end. Greenland's cores show it as a series of jagged spikes, abrupt warmings followed by brutal reversals. Antarctica's version is a slow, steady climb, like an elevator rising methodically, while Greenland's climate takes the stairs two at a time, then trips. Yet when you line up these records side by side, something extraordinary emerges. During major global events like the transition out of the last ice age, Antarctica's warming actually leads Greenland's by a few centuries. It's as if the South gets the memo first, then nudges the North through oceanic and atmospheric connections. This lag isn't a bug in the system. It's a feature, revealing how Earth moves heat between hemispheres like a relay race passing a baton. The ice cores show this handoff in exquisite detail. Antarctic temperatures rising as the South absorbs extra sunlight due to orbital cycles, followed by carbon dioxide released from warming oceans, which then amplifies heating globally, finally triggering Greenland's abrupt jumps. The implications are profound. These hemispheric mismatches prove that climate change doesn't blanket the planet uniformly. It ripples across latitudes and longitudes, driven by feedbacks we're only beginning to map. Today, as Greenland's ice sheet melts at record speeds and Antarctic glaciers destabilize, the past whispers a warning. When one hemisphere stumbles, the other eventually follows. The cores remind us that climate stability is a delicate illusion, a temporary truce between forces that, left unchecked, can tip the entire system into a new state. And that's the real value of comparing these frozen archives. They don't just record history, they teach us how Earth's pieces fit together and what happens when we shake the board. The ice cores dating back 20,000 years tell the story of a planet utterly transformed, a world where glaciers stood taller than skyscrapers, where New York City lay buried under a mile of ice, and where the sea retreated so far that you could walk from Siberia to Alaska without getting your feet wet. This was the last glacial maximum, the peak of Earth's last ice age, and the frozen layers from this era are some of the most revealing pages in our planet's climate diary. What they show isn't just a snapshot of extreme cold, it's a roadmap of resilience, documenting how Earth clawed its way back from the brink of deep freeze. Take a single ice core from Greenland, and you'll find oxygen isotopes signaling temperatures 10 degrees Celsius colder than today, while trapped air bubbles reveal carbon dioxide levels scraping rock bottom at 180 parts per million, so low that plants struggle to photosynthesize. Dust concentrations in these layers tell their own tale. With so much water locked up in ice sheets, deserts expanded wildly, and fierce winds carried their grit thousands of miles before dumping it onto glaciers. Yet even in this frozen desert, life persisted. Microbes hibernated in the ice, while hardy grasses and shrubs clung to the edges of ice sheets, waiting for their moment. The real drama begins when these cores reveal the thaw. Unlike the steady cooling that led into the Ice Age, the warming that ended it came in fits and starts, a series of violent lurches punctuated by sudden reversals. In Greenland's ice, you can see these abrupt shifts etched like jagged lightning bolts, temperatures soaring 8 degrees in a decade, then crashing back down just as fast. Scientists call these events Disentangling cycles, and they're thought to be linked to collapses of the North Atlantic circulation system, a reminder that Earth's climate doesn't always change gradually. Sometimes it staggers like a sleepwalker jolted awake. What's astonishing is how these northern upheavals played out globally. Antarctic ice cores show a different rhythm, slower, steadier warming, but when compared to Greenland's records, they reveal a planetary tag team. As Antarctica began warming first, its rising temperatures released carbon dioxide from the Southern Ocean, which then seeped northward, amplifying Greenland's abrupt jumps. It's a breathtaking example of Earth's interconnectedness, a nudge in the south rippling across hemispheres, turning local shifts into global transformations. But the most crucial lesson from these icy archives isn't just how the Ice Age ended, it's how long it took. Even after warming began, the planet needed thousands of years to fully emerge from the cold. Ice sheets the size of continents didn't vanish overnight. They retreated in fits and starts, their meltwater occasionally triggering new cold snaps as they flooded the oceans. The parallels to today are impossible to ignore. While humanity's greenhouse gas emissions are warming the planet 100 times faster than natural cycles, The Ice Age's recovery reminds us that climate change isn't a switch to flip, it's a cascade of dominoes, each one tipping the next in ways we're still learning to predict. Hidden in these ancient layers is a paradox. The same forces that buried the planet in ice also set the stage for civilization's rise. As the glaciers retreated, they left behind fertile soils, filled basins with freshwater lakes, and opened migration routes for early humans. The Ice Age wasn't just an obstacle, it was a crucible shaping the world we inherited. And as we drill deeper into these frozen records, we're not just studying the past. We're reading a survival guide for the future, written in isotopes and dust by a planet that's seen it all before. The frozen archives don't just record air temperatures, they hold secrets about the oceans too. Hidden within the intricate chemistry of ancient ice are clues to how high, or how low, the seas once rose, painting a picture of Earth's coastlines as they shifted across millennia. When massive ice sheets melted during past warm periods, they didn't just vanish quietly. They sent torrents of freshwater rushing into the oceans, leaving behind chemical fingerprints in the ice that scientists can now read like tidal marks on a geological dock. These meltwater pulses weren't gentle transitions, they were planetary upheavals capable of rewriting maps in geological minutes and sending climate systems into chaos. One of the most dramatic examples comes from layers dating to 14,600 years ago, when Earth was shaking off the last ice age. Ice cores from Antarctica show a sudden spike in oxygen isotopes, a telltale sign of warming, while sediment cores from the ocean floor reveal corresponding layers of coarse gravel dumped by raging meltwater rivers. This was Meltwater Pulse 1A, a global deluge that raised sea levels by 20 meters in less than 500 years. To put that in perspective, it's like watching the Statue of Liberty's torch dip underwater within a human lifetime. The ice cores capture this event not just through chemistry, but in the very texture of the layers. Bands of cloudy ice formed under pressure as glaciers slid toward the sea, their final moments frozen in time. But the real revelation lies in how these ancient floods linked to climate chaos. When all that freshwater poured into the North Atlantic, it didn't just raise sea levels, it disrupted the ocean's conveyor belt of currents, including the Gulf Stream. Greenland's ice cores from this period show temperatures plummeting even as the rest of the planet warmed, a climate paradox triggered by the ocean's sudden identity crisis. It's a pattern we've seen repeatedly in the ice, meltwater pulses followed by climatic whiplash, where one region floods while another freezes. Fast forward to today, and these frozen warnings take on new urgency. Modern satellites measure Greenland and Antarctica losing ice at rates that, while still slower than Meltwater Pulse 1A, are accelerating alarmingly. The difference, past pulses unfolded over centuries, giving ecosystems and civilizations time to adapt. Today's rise is happening decades, not millennia, and the ice cores suggest we're tampering with a system capable of violent overcorrection. Hidden in those ancient layers is a simple truth. When ice sheets crumble, they don't ask permission, they rewrite the rules. And as we drill deeper into these frozen records, we're not just studying history. We're reading the first drafts of our future coastline. The same ice cores that reveal ancient climates also hold traces of human desperation and ingenuity, chemical echoes of moments when the weather turned against entire civilizations, forcing them to migrate or reinvent their ways of life. Take the layer of volcanic ash dating to 74,000 years ago, when Indonesia's Toba super eruption choked skies worldwide. Ice from this period shows sulfur levels spiking, followed by a dramatic cooling that likely lasted decades. Around this same time, genetic studies suggest human populations shrank to just a few thousand breeding pairs, a bottleneck that may have pushed our ancestors to the brink. The ice tells us why, with sunlight dimmed and temperatures plummeting, survival meant moving or adapting, and those who couldn't perished where they stood. Fast forward to more recent layers and the pattern repeats. Around 12,800 years ago, as the Younger Dryas cold snap gripped the northern hemisphere, ice cores register a sudden drop in methane, a sign of shrinking wetlands and drying landscapes. Archaeological records from this period show hunter-gatherer societies across the Middle East abandoning their traditional grounds, some migrating toward emerging river valleys where water still flowed. These weren't aimless wanderings, they were strategic retreats etched into the land like footprints in mud. The ice preserves the climate shock that triggered them, while stone tools and hearths left behind mark the human response. Perhaps the clearest example comes from layers corresponding to the 4.2 kiloyear event, a megadrought around 2200 BC that left its mark in ice cores from the Andes to the Himalayas. Isotopes in these layers tell of failed monsoons and withered rivers, while dust concentrations spike like a fever chart. Down in the archaeological record, the consequences are stark. The Akkadian Empire in Mesopotamia collapsing as crops failed, the Indus Valley cities emptying as wells ran dry. Yet amid this chaos, some communities thrived. Along the Nile, where flood patterns shifted but didn't vanish, Egyptian pharaohs consolidated power, their grain stores buffering against the drought. The difference wasn't just luck, it was adaptation, a lesson written in both pottery shards and ice-bound chemistry. Today, as we face our own era of climate upheaval, these frozen archives offer more than just history, they provide a mirror. When Greenland's ice shows Norse settlers in the Middle Ages clinging to failing farms as temperatures dropped, their livestock starving and soil freezing, we see a warning about inflexibility. Contrast that with the Inuit, who shifted from farming to sea ice hunting as the same cold snap made new resources available. The ice doesn't judge these choices, it simply records their outcomes. And what it suggests is unsettlingly clear. Civilizations that bend with the climate often survive, while those that resist it frequently fracture. The most profound lesson, though, lies in the scale of these ancient disruptions. Past migrations and collapses were triggered by shifts we'd now consider minor, a degree or two of cooling, a few decades of drought. Yet they upended societies with far simpler infrastructures and smaller populations than ours. As ice cores reveal carbon dioxide levels now soaring beyond any natural precedent, the question isn't whether we'll face climate-driven challenges, it's whether we'll heed the frozen archives whispering that survival has always been a dance with the elements, never a conquest. The next chapters of human migration are being written not in ice, but in the choices we make as the planet changes beneath our feet. The race to save Earth's frozen archives has become a desperate scramble against time. Across the globe, from the Andes to the Alps, glaciers that have stood for millennia are now retreating at speeds that leave scientists breathless, not just from thin mountain air, but from the sheer urgency of their mission. Every summer, meltwater carves new channels through ice that once held pristine records of ancient climates, washing away layers like pages torn from a history book. In Greenland, dark pools of meltwater now stain the ice sheet's surface, absorbing sunlight and accelerating the thaw. Even Antarctica, long considered Earth's most stable freezer, has seen glaciers like Thwaites, nicknamed the Doomsday Glacier, begin to hemorrhage ice at alarming rates. The irony is cruel, as warming makes these climate records more crucial than ever to understand. It's also ensuring their destruction. What's vanishing isn't just ice, it's entire chapters of Earth's story. Some of the most vulnerable records are high-altitude glaciers in the tropics, like those on Kilimanjaro or in the Himalayas. These icy sentinels have captured regional climate patterns for tens of thousands of years, preserving details about monsoon cycles and atmospheric circulation that exist nowhere else. Yet as temperatures rise, their upper layers melt first, erasing the most recent millennia of data, the very period when human civilization flourished and began reshaping the planet. One team working in the Peruvian Andes found that a glacier they'd cored in the 1990s had lost its entire top 20 meters by 2015, wiping out a climatic record stretching back to the Roman Empire. The scientific response has been a mix of ingenuity and heartbreak. Expeditions that once planned methodical, years-long drilling campaigns now operate like emergency crews, prioritizing glaciers deemed most at risk. In Switzerland, researchers used helicopters to airlift ice cores from the Corbusier Glacier just before a heat wave turned its surface to slush. Others employ thermal drones to map thinning ice sheets, identifying the last intact pockets of ancient snowfall before they liquefy into rivers. But even these heroic efforts can't salvage everything. Some ice, like that from Bolivia's Chacaltaya Glacier, once the world's highest ski resort, is already gone, taking with it unique records of Amazonian rainfall patterns and pre-colonial air quality. The loss extends beyond climate data. Ice cores from melting glaciers have revealed unexpected treasures, like ancient plant fragments from eras when these frozen peaks were green valleys, or industrial pollutants tracing the rise and fall of forgotten empires. A core drilled from Mongolia's Gulaya ice cap contained bacteria frozen for 15,000 years, offering clues about how life adapts to extreme environments. As these time capsules dissolve, they're not just erasing atmospheric history, they're destroying a library of biology, chemistry, and even human culture preserved nowhere else on Earth. Perhaps the most haunting realization is how recent this crisis has become. Photographs from early 20th century expeditions show explorers posing beside glaciers that have since retreated miles up valleys. Ice that took 15,000 years to form has vanished in 15 human lifetimes, and while scientists can sometimes shift their focus to colder, higher altitude sites, those too are now under threat. The window for collecting some cores, particularly from mid-latitude glaciers, may have already closed forever, leaving gaps in our understanding of how regional climates respond to global shifts. Yet amid the urgency, there's a quiet revolution in how we study these disappearing archives. Teams now scan glaciers with ground-penetrating radar before drilling, creating 3D maps to prioritize the most information-rich layers. Some researchers experiment with virtual ice cores, using machine learning to fill gaps in damaged samples by comparing them to intact records from similar regions. Others focus on preserving what they can't collect, documenting meltwater chemistry and isotopic signatures before they're lost to rivers and oceans. These efforts won't replace the lost ice, but they might salvage fragments of its story. The tragedy unfolding in these frozen vaults isn't just about science, it's about memory. For millions of years, Earth's ice has been a meticulous archivist, recording every atmospheric sigh and climatic tremor. Now, as we finally learn to read its language, the archives themselves are crumbling. Each lost layer is more than data. It's a testament to our planet's resilience through asteroid impacts, supervolcanoes, and natural climate swings. And as the ice retreats, it leaves us with a question we can't afford to ignore. If we fail to protect these frozen memories, how will we ever understand the changes yet to come? Science is rarely a monolith, and ice core research is no exception. While these frozen archives provide astonishingly detailed records, interpreting their clues has sparked fierce debates that cut to the heart of how we understand Earth's climate story. One ongoing controversy centers on whether ancient carbon dioxide levels were as stable as ice cores suggest. A small but vocal group of researchers points to alternative proxies, like fossilized plant pores called stomata, that occasionally show higher CO2 concentrations than those recorded in bubbles from the same period. They argue that under certain conditions, ice might not perfectly preserve atmospheric gases, potentially skewing our view of past climates. Other scientists counter that these discrepancies likely reflect local variations rather than global averages, emphasizing how ice cores from Antarctica and Greenland consistently align across vast distances. The causes of abrupt climate shifts have also divided experts. Greenland's ice cores clearly show dramatic temperature swings during events like the Younger Dryas, but what triggered them remains hotly contested. Some teams argue for a cosmic impact as the primary driver, pointing to layers with unusual platinum and nanodiamond concentrations. Others insist these markers could have terrestrial origins, like volcanic eruptions or even wildfires. The debate isn't just academic, it's about whether our climate system is more sensitive to external shocks or internal feedback loops, a distinction with huge implications for predicting future changes. Even the iconic hockey stick graph of modern warming, partly built on ice core data, faces scrutiny. Critics question whether statistical methods used to combine proxy records might underestimate natural variability, while defenders highlight how independent lines of evidence, from tree rings to coral growth, consistently reinforce the ice core's testimony. These disagreements aren't weaknesses in the science, they're the engine of discovery, pushing researchers to test hypotheses with ever more precise instruments. What's remarkable is how these debates unfold not in shouting matches but through painstaking detective work. When one team suggested that meltwater might alter ice core chemistry, others responded by drilling in drier, colder sites to compare results. When questions arose about gas diffusion in ancient ice, labs developed new techniques to analyze molecules at microscopic scales. This self-correcting process is science at its best, where every challenge sharpens our tools and deepens our understanding. The takeaway isn't uncertainty but progress. Disagreements force researchers to ask tougher questions, design cleverer experiments, and ultimately build a more nuanced picture of Earth's past. And as new drilling technologies reach even older ice, like the ongoing hunt for million-and-a-half-year-old samples in Antarctica, these debates will continue refining our grasp of how fragile our climate balance truly is. Far from undermining the value of ice cores, these controversies prove just how vital they remain in our quest to comprehend the forces that shape our world. The next frontier of ice core research isn't just about drilling deeper, it's about rewinding Earth's climate clock to an era before the ice ages as we know them even began. Teams in Antarctica are now pioneering radical new drilling technologies, from hot water jets that slice through millennia in hours to lasers that can analyze ice chemistry without melting a single flake. Their target, ice buried nearly 3 kilometers below the surface, dating back 1.5 million years to the mid-Pleistocene transition, a mysterious period when Earth's climate rhythm inexplicably slowed. Before this shift, ice ages came every 41,000 years like clockwork. Afterward, they stretched to 100,000 years. The cores being chased today might finally reveal why. What makes this quest so revolutionary isn't just the older ice, it's the quantum leap in how we'll study it. Traditional drills could only retrieve cores in meter-long segments, risking contamination between layers. New pressurized drills now capture continuous ice columns while maintaining the sample's original atmospheric pressure, preserving gases that have eluded scientists for decades. Meanwhile, quantum sensors capable of detecting single molecules promise to uncover trace compounds, everything from ancient wildfire smoke to rare isotopes that previous technology missed entirely. Imagine reading not just Earth's temperature history, but its atmospheric recipe book in ingredients we never knew to measure. The stakes couldn't be higher. Layers from the mid-Pleistocene likely hold clues to why our planet's climate sensitivity changed so dramatically. Some theories suggest shifting ocean currents or CO2 thresholds tipped the system into a new state. Others point to gradual erosion of mountain ranges altering wind patterns. The answers may rewrite our understanding of how close or how far we are from pushing Earth into another irreversible transition. Already, early samples from near the transition show carbon dioxide levels never exceeded 300 parts per million during warm periods, a sobering contrast to today's 420 and climbing. Perhaps most tantalizing are the biological secrets waiting in this ancient ice. At these depths, researchers expect to find microbes frozen long before modern humans evolved, possibly representing lost branches of Earth's tree of life. Their survival strategies could redefine the limits of life itself and offer hints about organisms that might thrive in the icy oceans of Europa or Enceladus. Other teams are developing cryo-electron microscopes that can flash freeze samples mid-analysis, capturing cellular structures in their pristine state for the first time in millions of years. Yet this golden age of ice core science faces a cruel deadline. As warming temperatures compromise older ice near the surface, scientists are racing not just to drill, but to decode these archives before natural melt distorts their chemical fingerprints. Some projects have turned to AI, training algorithms to predict where the oldest, most undisturbed ice still lies hidden beneath Antarctica's shifting glaciers. Others are creating backup repositories, preserving duplicate cores in polar vaults where they'll outlast the very glaciers they came from. What emerges from these next-generation cores won't just fill gaps in climate models, it will test their predictions against real-world experiments from Earth's past. If models can accurately retrodict the climate shifts recorded in million-year-old ice, we'll know we're on the right track for forecasting what comes next. If they fail, it's back to the drawing board with humbling new constraints. Either way, these frozen time capsules are about to take center stage in the greatest detective story of all, how a planet's climate evolves and what it means for those of us living through its latest chapter. The frozen archives hold a mirror to our current climate crisis, and the reflection is impossible to ignore. Those tiny bubbles of ancient air trapped in ice cores tell an unequivocal story. Today's carbon dioxide levels, soaring above 420 parts per million, eclipse anything seen in the last 800,000 years. Not by a little, by a staggering margin. The highest natural peak over that near million-year span was around 300 parts per million during warm interglacial periods. We've now blown past that benchmark as if it were a quaint relic, adding another 120 parts per million in barely more than a century. The pace is geological whiplash, a vertical spike on the graph where past changes curved gently over millennia. What makes this surge so alarming isn't just the number itself, it's how drastically it departs from Earth's established rhythms. For 8 glacial cycles, the ice cores show CO2 and temperature moving in lockstep, rising and falling within a predictable band. Warm periods never exceeded that 300 parts per million ceiling, while ice ages bottomed out near 180. This was the planet's comfort zone, a range that supported everything from sprawling grasslands to complex civilizations. Now we've left that zone behind, conducting an experiment with no precedent in the ice core record. Even more unsettling, the last time CO2 was this high, during the Pliocene 3 million years ago, sea levels were 20 meters higher and camels wandered a forested Arctic. The ice didn't forget those conditions, it preserved them as a warning. But the cores reveal something equally critical about how Earth responds to change. Past CO2 increases, driven by natural feedbacks like ocean warming or permafrost thaw, unfolded over thousands of years. Ecosystems had generations to adapt, migrate, or evolve. Today's rise has happened roughly 100 times faster, outpacing even the most abrupt natural shifts in the record. Take the Paleocene-Eocene thermal maximum 56 million years ago, a geological blink when CO2 spiked and temperatures soared 5 degrees Celsius. That event, often cited as an analog for modern warming, still unfolded over 10,000 years, a leisurely stroll compared to our current sprint. The ice cores remind us speed matters. When change outpaces adaptation, the results are chaos, collapsing food webs, destabilized weather patterns, and ecosystems scrambling to cope. Perhaps the most urgent lesson from these frozen time capsules is about thresholds. Ice cores from Greenland show that Earth's climate doesn't always shift smoothly. It lurches, flipping between states when pushed past invisible tipping points. The Younger Dryas, that violent cold snap 12,000 years ago, proves how quickly the system can reconfigure itself. Regional temperatures plunging 10 degrees in a decade after freshwater flooded the North Atlantic. Today, we're poking at similar levers, melting permafrost releasing methane, darkening ice sheets absorbing more heat, rainforests drying into tinderboxes. The difference, we're pulling all these levers simultaneously, with a planet now packed with 8 billion people reliant on stable climates for survival. Yet the ice archives also offer a sliver of hope. They document moments when humanity's collective action left measurable marks, like the sharp drop in lead pollution after bans on leaded gasoline, or the recovery of the ozone layer following the Montreal Protocol. These successes, etched in the ice alongside our mistakes, prove that policy shifts can alter our environmental trajectory. The challenge now is scaling those efforts to match the unprecedented magnitude of modern warming. Because the ultimate lesson from the ice cores isn't just about danger, it's about agency. For the first time in Earth's history, a species holds the power to consciously steer the climate's course. The next layers being formed right now will record whether we rose to that responsibility or let the moment slip through our fingers like melting snow. The race to protect Earth's vanishing ice archives has become a scientific moonshot, one that demands not just urgency but unprecedented global cooperation. Across the polar regions and high mountain glaciers, teams are working against the clock to extract and preserve ice cores before rising temperatures erase them forever. This isn't just about saving ice, it's about safeguarding humanity's longest continuous record of our planet's climate history, a library of frozen data that took hundreds of thousands of years to compile and could vanish in mere decades. One ambitious project, the Ice Memory Initiative, reads like a climate-themed heist film. Scientists from over 20 countries are identifying the most vulnerable glaciers, then extracting meter-long cores to be shipped under strict temperature controls to Antarctica, nature's ultimate deep freezer. There, in a specially built vault dug into the snow at the Concordia Research Station, these icy time capsules will be stored at -50 degrees Celsius, preserved for future generations even if their original glaciers disappear entirely. It's a backup plan for Earth's memory, ensuring that researchers in the year 2100 or beyond will still have pristine samples to study, long after the last alpine glaciers have melted into history. But preservation goes beyond physical storage. Advanced 3D scanning techniques now allow teams to create digital twins of ice cores, capturing every layer and bubble in micrometer resolution. Laser spectrometers can analyze isotopes on site, beaming data to servers halfway across the world before a single sample melts. These efforts create redundant records because when it comes to climate data, losing a single core could mean erasing thousands of years of atmospheric history that exist nowhere else. The stakes extend far beyond academia. Indigenous communities from the Andes to the Arctic rely on glaciers for freshwater, cultural heritage, and spiritual connection. Their traditional knowledge often corroborates what the ice reveals: stories of hunting grounds that vanished with the snow, or ancestral paths now drowned under meltwater. By preserving ice cores, scientists aren't just archiving climate data, they're helping safeguard living histories that connect people to landscapes undergoing radical transformation. Yet the greatest challenge may be political, not technical. Ice sheets don't respect national borders, and protecting them requires cooperation between nations that don't always agree. Remarkably, Antarctica has set a precedent. The Antarctic Treaty System has kept the continent demilitarized for decades, proving that science can sometimes transcend geopolitics. Similar frameworks are now being proposed for the Arctic, where melting ice is opening new shipping routes and new tensions even as researchers scramble to document its disappearing climate records. What makes these preservation efforts so vital is their time sensitivity. Unlike archaeological digs or fossil hunts, where artifacts remain buried until discovered, ice cores are actively disintegrating in real time. Every summer melt season irrevocably alters their chemical signatures, blurring the very data we need most to understand our climate future. The work happening now in remote field camps, high-tech labs, and diplomatic meetings isn't just about curiosity. It's about ensuring that when future generations ask how we let the planet warm, the evidence won't have already melted away. The ice has kept its records faithfully for millennia. Now it's our turn to keep them safe. The frozen secrets once locked away in remote ice sheets are now stepping into the spotlight, thanks to a wave of museums and documentaries bringing this groundbreaking science straight to the public. Walk into the Natural History Museum in London or the Smithsonian in Washington, and you'll find entire exhibits built around ice core slices, translucent cross-sections backlit to reveal their delicate layers, each stripe annotated with events from human history. These displays don't just showcase the ice, they transform it into a tactile timeline, letting visitors run their fingers along grooves marking the rise of agriculture, the fall of empires, or the start of the Industrial Revolution. Interactive screens zoom in on single bubbles, releasing virtual pop-ups that explain how a speck of dust from a Mongolian drought or a trace of lead from Roman smelters ended up trapped in Antarctic ice. It's climate science made visceral, no lab coat required. Documentaries have taken the immersion even further. Recent productions like The Secrets in the Ice use cinematic techniques straight from forensic thrillers, time-lapse shots of drills piercing deep into glaciers, microscopic views of ancient air bubbles bursting open after millennia, even CGI recreations of prehistoric storms based on isotopic data. The effect is revelatory. Suddenly, abstract concepts like parts per million or feedback loops become dramatic narratives, with ice cores as the silent witnesses to Earth's most pivotal moments. One standout scene from a BBC Earth special recreated the Younger Dryas' cold snap as a detective story, using ice core graphs like clues in a planetary whodunit. By framing science as storytelling, these films do more than inform. They make audiences feel the urgency of climate history unfolding in real time. Behind this push for accessibility is a profound shift in how scientists communicate their findings. Glaciologists who once published primarily for academic journals now routinely consult with museum curators and filmmakers, translating complex data into relatable analogies. A favorite, comparing Earth's atmosphere to a bathtub, ice cores show how, for hundreds of thousands of years, the drain natural CO2 absorption kept pace with the faucet volcanic emissions and respiration. Now, humanity's burning of fossil fuels has cranked the faucet wide open, while deforestation has clogged the drain. Simple, vivid, and impossible to unsee once you've encountered it beside a display of ice cores spanning that very transition. The impact ripples beyond casual learning. Teachers from Oslo to Sydney now use ice core data in classrooms, with students graphing CO2 concentrations from bubble records or debating climate policy based on past warming events. Citizen science projects invite volunteers to help classify dust particles in core samples via online platforms, democratizing research that was once confined to elite labs. Even gaming has gotten in on the action. One indie developer created a simulation where players balance energy use against ice melt rates, with core-derived climate models governing the game's physics. What makes this public engagement so vital is its timing. As glaciers vanish at record speeds, their disappearing archives underscore a paradox. We're finally learning to read Earth's climate diary just as the pages are burning. Museums and media bridge that gap, ensuring these discoveries don't stay siloed in academia but become tools for collective understanding. When a teenager in Mumbai sees an ice core exhibit linking monsoon shifts to ancient droughts, or a retiree in Toronto watches a documentary connecting medieval lead pollution to modern air quality standards, climate change stops being a distant threat and starts feeling like a story we're all living and writing together. The ice has kept its records faithfully. Now it's our turn to listen and to act. The ice walls of Greenland and Antarctica are more than frozen landscapes. They are time machines revealing Earth's climatic soul. Layer by layer, they've preserved the planet's heartbeat, capturing every gasp of warming and every shudder of cooling across nearly 1 million years. These archives don't just belong to scientists. They're humanity's shared inheritance, a chronicle of resilience and fragility written in isotopes and dust. And now, as temperatures rise and these frozen libraries crumble, their warnings grow louder. The past they reveal isn't a distant curiosity. It's a mirror reflecting back the consequences of disrupting systems we're only beginning to understand. Consider the speed at which we're unraveling Earth's climate story compared to how long it took to write it. The ice cores show that natural shifts unfolded over millennia, giving ecosystems and civilizations room to adapt. The rise in greenhouse gases that once took 5,000 years now happens in 50. That's the difference between a gentle slope and a cliff edge, and we're sprinting toward the drop. Yet within this urgency lies an extraordinary opportunity. For the first time in history, a species can read its planet's memoirs while there's still time to change the ending. What makes these icy records so profound is their impartiality. They don't debate or politicize, they simply testify. When bubbles from the last interglacial period show carbon dioxide peaking at 280 parts per million compared to today's 420, the message is inescapable. When dust layers from ancient droughts align with archaeological evidence of collapsed civilizations, the connection demands attention. These aren't projections or models, they're receipts stamped by time itself. And they prove something revolutionary. Climate change isn't a future threat. It's an ongoing story, one we've been inadvertently writing since the first coal-fired steam engines hissed to life. But the ice cores also offer hope. Hidden in their layers are tales of recovery, periods when ecosystems rebounded, when innovations flourished in the face of change. The ozone hole didn't heal by accident. It shrank because the world listened to Antarctic ices warning about CFCs and acted. Lead pollution didn't vanish from Greenland's ice because of market forces. It faded because science and policy aligned to remove it from gasoline. These victories, preserved in the ice alongside our mistakes, prove that course corrections are possible when knowledge meets collective will. As these frozen archives melt, they leave us with a choice. Will we be the generation that preserved their lessons or the one that let them slip away? The next chapters of Earth's climate story are still being written, not in ice, but in the choices we make about energy, conservation, and innovation. Every policy enacted, every technology adopted, every patch of forest protected becomes part of the record future generations will study. The question is whether they'll see our era as a turning point or a cautionary tale. So let these discoveries ignite more than curiosity, let them spark action. Whether it's supporting climate research, advocating for sustainable policies, or simply sharing these stories to widen their reach, we all hold a pen in rewriting what comes next. The ice has spoken, now it's our turn to listen. Drop your thoughts in the comments below. What fascinates you most about Earth's frozen time capsules? And don't forget to subscribe for more journeys into the mysteries that shape our world. The past isn't finished teaching.